Swayam Prabha. Digital India. Educated India.
We come back to our discussion on internal energy. It is a quantity that has been defined in terms of the first law of thermodynamics, and that was something like this, that if dq amount of heat enters into the system, say dq amount of heat enters into the system. Note that I have used this word, this imperfect differential, with small quantities only, and that enters into the system, and the system does some amount of work dW, again imperfect differential. This difference can be equated to a quantity d of E, that is change in internal energy of the system. So internal energy is something very important, and that related to heat flow and the work flow across the boundary of a system. And this is the first law that we have learned so far. And E is a property. So if I go into the more details about this work, so dW is a work that is a mechanical work that we have shown that dW is basically a P opposing pressure that is being opposed against a change of volume dV. So this is a mechanical work. On that matter. So basically this is dE equal to dQ minus P opposing type times dV. Now if I write this quantity, now if I consider a constant process, constant volume process, that means I keep V constant. That means I am putting a restriction on the process in such a way, then dE at, put a subscript here to make this is a 0, and this is equal to basically dQ at constant volume, because dV is basically 0. Now we know also, this is purely from the first law, that we have got this condition. So change in internal energy at constant volume is equal to the heat that has been put into the system at constant volume. Now internal energy is basically a function of temperature and volume, function of two variables, because we are interested in a function of two variables to define the state of a system. So E, internal energy, is a function of two variables, say temperature and volume. Then any change dE, that is equal to del E del T at constant volume plus del E del V at constant temperature times dV. So this is purely from the definition. These two have nothing to do with the first law. This is the conclusion derived from the first law, that, and putting a restriction on the change in volume, that I keep volume V constant. Now that means that now if I write the internal energy as a function of two variables, for any function of two variables, for dt, dt. So the del E del T taken at constant volume times dt, and del E del V at constant temperature with respect to that volume, change in volume. So these are the quantities. Now you can see that this gives you, again, if I take the same thing, there is a constant V constant, keep V equal to constant, then what this means is del E del V, and that is del E del T at constant volume times dt, because dV is 0. This is purely from the definition of this function of two variables. Now this is the first law, and if I can relate these two, I can see that dq from these two, from 1 and this is 2, I see this gives me a simple thing, that is dq v, that is equal to del E del T at constant volume times dt. This is the differential of a function E with respect to t at a constant volume, and this is dt. So if I differentiate this dq constant v dt, if I take a derivative like this, then that is del E del T at constant volume. Now we know this is a quantity which is not difficult to understand. It means that this is the amount of heat that is being absorbed per unit rise in temperature at a constant volume. So it is a quantity that we know, that is called the specific or the thermal heat capacity, or specific heat at constant volume. This quantity we know purely from the phenomenology, that this is basically the specific heat at constant volume. So that means the system takes up heat at per unit rise in temperature, amount of heat taken by a system per unit rise in temperature. That is the specific heat. And now you see that del E is an internal property as it changes with temperature, del E del V. So these two are related in this way. So if I call this a specific heat CV, that is equal to del E del T at constant volume. This is the specific heat at constant volume, is related to the change of internal energy with temperature at a constant volume. So this is a property defined in terms of another property. So internal energy is defined, that defines your specific heat of the system. Specific heat is a property of the system. So internal energy is something that helps us to understand what is the specific property, because it is a property of a system, and this is not the property of a, this is not a property of systems. Once I can relate this to this quantity, this becomes, CV becomes a property of the system, because dq is not a property. dq is something, the heat that is being absorbed by the system and per unit rise in temperature. Nobody knows that it has how it is related to the internal energy or something. But this is when this is related by the, because of the first law, then that defines my specific heat in a very specific way. It's a very specific way of defining, or more accurate way of defining the specific heat. So this is a phenomenological definition that we normally use in the class 12 curriculum, and this is something that seriously takes the picture to the thermodynamic level. Now, so far so good. So now del E is a change of property of a system dE, which is then this is basically Cv times dt, plus there is another quantity del E del V at constant temperature times del dV. So if this is a property times the dt, the change in temperature, property of the system, this is a change in property of a system. So I also anticipate that this is also a property of the system, del E del V. So what this quantity is? What this quantity is? What is this? So it is a property. I can anticipate a property of the system, but still it is not clear from this definition that what this really means, what sort of property it is. So for that, to understand what this del E del V, rate of change of internal energy with respect to volume at a constant temperature, and what this quantity is a question. So to answer this question purely from the experimental point of view, Joule again come back to an experiment. So the experiment is a famous experiment that is called the JOULE'S experiment. So we come to JOULE'S experiment, and JOULE'S experiment is something like this. You take a bilobal container, there are two lobes of the container, A and B, say it is A and this is B, and there is a stopcock in between. This is a stopcock arrangement, and what I can, if I close this stopcock, the two compartments are separated. I fill the gas, I say initially I fill the gas with A at a constant temperature. So I fill the gas, some gas, initially there is I put a gas. So initial state is this A filled up with a gas, and I need to put up everything in a bucket of large heat bath, and I put a thermometer here. This is a thermometer. Now in the initial state we fill A is filled up with a gas and B is in vacuum. That is my initial state. Now what I do, I keep this at a particular temperature in a heat bath, and then what I do, I open this top, then allow the gas to pass into the bulb, into this lobe B, and both the compartments are filled up with the gas. So in the final state, A gas fills up A and B uniformly, and I see whether I try to see what is the rise in temperature in the gas. So the idea is to see that I allow the gas to expand against a vacuum. So when the gas is expanding against a vacuum, there is no work because there is no external opposing pressure to expand. So by construction, the gas expands against zero pressure. That means dW is basically P opposing times dV. There is a change of state. This is positive quantity, but this P itself is 0, 0 times dV, and this is 0. So there is the system does not do any work. So that dW is 0. So if we now apply the first law, that is dE equal to dQ minus dW, and also since E is a function of temperature and pressure, then dE by temperature and volume, then Cv times dt, that we have already written, and that is my del E del V at constant temperature times dV. Then I see that so gas expands at zero pressure, and an important observation is this. So this, because of, since this is 0, since this is equal to 0, it gets simplifies to dQ equal to Cv dt plus del E del V at constant temperature dV. So dQ is basically this quantity. Now there is a change in volume. This is always positive. Now important observation in the experiment, that there is a thermometer here, and when the gas expands, Joule observed no change in temperature. Joule observed no change in temperature in the bath. That means in this bath there is no change in temperature. Since there is no change of temperature, so dQ, this means, this implies two things. dQ is equal to 0. That means no heat has entered into the system, and also since there is no change in, there is no heat change, and there is no change in temperature, this one dt is also 0. No change in temperature. So since there is no change in temperature, there is no heat is transferred into the system, and also dt is equal to 0. So means this is equal to 0, this is equal to 0. So means 0 equal to del E del V at constant temperature times dV. That is, in that case, dV not equal to 0. Therefore, del E del V at constant temperature equal to 0. So this is something, a property that Joule observed for the gas, observed for a gas which is basically an ideal gas. I will come to this, that why it is 0 in the case of ideal gas. We will come to that later on. But experimentally it was observed he could not observe any change in temperature. That immediately shows that there is no heat transfer between the system and the bath. So both dq 0, dt 0, and that makes everything 0 except this one. And so this means that this is also equal to 0. So ultimately, this is a property that we tried to understand. So we know that this is 0 for this particular case on this, that is for a gas when you have a very low density and at relatively higher temperature. So in that case, and also maybe the detection system was such that he could not really follow the change in temperature. But for real gas, this is this del E del V at constant temperature is not equal to 0 and has a small value. So it is mainly for an ideal gas, and we will learn more about it in future. That's why for ideal gas this is really equal to 0. But so far the experimental observation is concerned regarding this del E del V, and as it is plugged in an expression for change in dE, change in internal energy, that is something we need to understand this one. And so this is another quantity. Now we have fully understood the change in internal energy. Energy has something to do with some property specific heat at constant volume times that change in the temperature, and this is equal to 0. And for ideal gas, this is a very simple relation, that is for an ideal gas you have dE equal to Cv times dt only, and because this is equal to 0. But that is a very special case, not that in all cases this is equal to 0, and it has del E del V has some more important expression, and which we will call the equation of state, and that will be derived when we will discuss the second law of thermodynamics. As a consequence of the second law, we will be able to derive its actual nature of del E del V. But for the time being, let us just have a look at the Joule's experiment. He tried to have a very preliminary understanding about this quantity, because it is a property of the system. He tried to understand that property, and he found that it is basically 0 for ideal gas. That was his conclusion. So far so good. And
specific amount of
yes, for definite amount of substance, of course. Important question is to understand the first law. When we keep the pressure constant, not the volume constant, so we will see what happens to that particular situation. So this is a constant volume situation that we worked out. Next we over to constant pressure situation. So change of state under constant pressure. That is pressure equal to constant. So we start with a very simple experiment. Experiment is the following. So at constant pressure, now we consider as usual a gas with a piston. Put a gas inside this enclosure, and this is the P opposing pressure, and it is at this gas is kept in a large heat bath. Heat bath is kept at a temperature T1. Heat bath is kept at a temperature T1. And this has a volume V1, and at equilibrium it attains the same temperature T1, and there is a pressure P opposing, and as it equilibrates there will be a pressure against it, the inside pressure that I can calculate from V1 and T1. And now what I do, I change the temperature from to another temperature, P opposing. This is the same pressure because we have kept the pressure constant, under constant pressure, and what we have changed in going from this figure to this figure, that temperature T1 is changed to T2, that is heat bath is now kept at a temperature T2, and the gas changes its volume to V2 at a temperature T2. Okay, so this is something, an experiment that we have done in this way, that it is a the volume, the small volume is kept here at a volume V1 is kept at a temperature T1 when I keep it in a everything in a heat bath, and the same thing I have under constant pressure condition, the same pressure condition that is, but the point is that it is at a higher temperature T2, so the pressure that is being opposed by it is something different here, but the external pressure that we have kept in both cases remains the same. So whatever changes are there because of some internal mechanism. So that T1 and T2, now we come back to that first law. So first law tells us that it is the change in internal energy delta E, that is E2 minus E1, that is basically Q amount of heat that enters into the system at constant pressure minus W. W is basically the work done. So at constant pressure, now for a constant pressure, you see that E2 minus E1, that I keep QP, a constant pressure constant, minus P opposing, and the system has changed its volume from V1 to V2. So V2 minus V1, this is a change, this is a work done by the system. So if I write this quantity in a slightly rearranged way, E2, I take that P times P opposing times V2 minus E1 plus P opposing times U1 equal to QP. Since everything has been done at a constant opposing pressure P, the opposing pressure is there constant level. Now you can see, now a very interesting thing is this, the P opposing, for this case, it is basically RT1 by V1, and this is the same as RT2 by V2, and that is equal to P1, and this is again T2 by V2, that is equal to P2. Note that P opposing is the external pressure that I have added into the system, and P1 and P2 are the internal pressures of the gas. They are equal because they are both are under equilibrium condition. Here it is in equilibrium, it is in equilibrium. Now we see, so therefore it is E2 plus P2 V2 minus E1 plus P1 V1 equal to QP. So that's a very interesting relation that you can see, and now we see that this quantity E2 plus E2 P2 V2 E1 plus P1 V1, I can write that as, if I write E some function H equal to E plus PV, then I can write this relation if defined. If we define, then it is H2 minus H1 equal to QP. So it is, so at constant pressure, the change in volume from V1 to V2 can be accounted for by a new function that is again an internal property of the system, because PV is a property and E2 is also a property of the system. PV is a property, and you can easily check that D of PV is a perfect differential, because this is equal to P dV plus V dP. This is a perfect differential. This quantity D of this is a perfect differential, but PdV and VdP individually are not perfect differential. So PV, D of PV is a perfect differential. E is also a perfect differential, and you can see that the totality in which we have H2 and H1, the difference is basically quantity. This is called, H is called, it is a special name, this is called enthalpy. So enthalpy is a property that crops up when we have a change of state at constant pressure. So I applied the first law, again applied the first law and the usual gas laws to define this particular quantity, and that gives me a very special kind of object, that is the heat gained by the system is basically at constant pressure is basically the change of an interesting property of this another property that is called the enthalpy. So for the QV, when it is QV, that is heat at constant volume, that is E2 minus E1, and here at Q at constant pressure is basically H2 minus H1. So there is some interesting connections between these things. I will try to work out of these relations further when I expand H as a function of temperature and pressure, and we'll see some new things that coming out of it, a new effect that are important also from the technological point of view. So with this I close, and thank you all for your kind attention.